as I hand this off to Jacob Knowles, Director of Sustainable Design at BR+A Consulting Engineers.
Rich, that was an awesome introduction and setting the context of why buildings matter, and we really do need to be moving to carbon neutral buildings. So let's talk about a couple of examples of how we've applied these kind of technology and strategies. So the first one is Chelsea Soldiers Home. It's a 250,000 square foot assisted living facility, has a full service kitchen. It's essentially if you took a hospital and you chopped off the patient bed tower, right, and just put that on its own site. It has to meet all the ASHRAE 170 air change requirements like a normal inpatient unit for a hospital. It has a reduced window to wall ratio, it has triple glazing, it has a 0.5 megawatt solar array canopy above the building. But the real trick of this is how are we getting off of fossil fuel? So in this case, we do have a geothermal loop, about 145 boreholes, 500 feet deep each. And that geothermal loop water, it's a closed loop system. It circulates between the ground loop and the building loop. And then the building loop goes to all of these different pieces of equipment that can pull heat out of that loop in the winter or reject heat into that loop in the summer. And so you can see at the top, we've got our dedicated outdoor air handlers that are providing ventilation. Those have heat pump compressors built into them so that they can heat and cool from that ground loop. We have at the zone level for each of the spaces, we have water source VRF. And then we also make domestic hot water from our heat pumps to eliminate fossil fuels for domestic hot water. So we'll walk through each of those pieces briefly. Now I keep mentioning the 500-pound gorilla for load reduction is the ventilation air in these types of high intensity buildings. So we have to really maximize our heat recovery from our exhaust air and capture that heat and put it back into the supply side. So this is a diagram here of our air handler. At the top, you can see the exhaust air leaving and it's going through a series of two wheels. You've probably heard of enthalpy wheel heat recovery. Well, this is a dual wheel system. You get even more effective heat recovery. And then the outdoor air on the bottom is coming in from the outside through the wheel, through the coil that does additional cooling in the summer or heating in the winter, and then through the second wheel. And so you're getting, in some cases, we're getting up to almost 80% effective heat recovery on these types of systems. So on a cold winter day, there's very little heat that you need to add to the air. Now, the other thing is people worry about heat pump systems being challenging to maintain, right? Normally think of a heat pump like a VRF system. You think of a bunch of condensing units out on the roof, right? A whole farm of condensing units for a big building. You have to go out on the roof on a snowy day and fix a piece of equipment that's failed to make sure you get some heat. Well, what we're doing here is very different. We're connecting VRF to the ground loop. So it's indoors. It's a water to refrigerant heat pump system, and each of those modules, those silver boxes stacked one on top of the other, is about 7 or 8 tons. So in the space of a stacked washer dryer, you can get 14 tons of heating and cooling, and it's all accessible indoors from a maintenance standpoint. And then for domestic hot water, again, you know, heat pumps are not cheap. So when you've got a system like domestic hot water that can have very high peak demands, but if everybody, not everybody, but if a large percent of people take showers at the same time, you're gonna have a lot of demand to heat that water up very quickly. So you could either put in a whole arsenal of heat pump chillers that connect from the ground loop into your domestic hot water loop, which is a very expensive approach, or you could put in a couple of modules like you see here on the left, and on the right, put in a series of thermal storage tanks, domestic hot water tanks that you can charge up and then discharge almost like a thermal battery. And then if you have a peak load, you can run both water from the tanks and from the heat pumps to boost it. And that generally will keep the boiler, the backup boiler, from kicking on at all. So through these strategies, we're able to drastically cut the energy consumption that would be the case for a normal building. So there's a lot of existing facilities like this that can be 150, 200 plus EUI, which is energy use intensity. Even the code baseline is over 100 EUI. So we have targeted a 55 approximately EUI for the proposed design. And then between the solar array on the roof and the future procurement of renewable energy credits from the grid, or also the greening of the grid over time, this building has the potential to achieve net zero. Now, it's, one might think, wow, we really must have broke the bank on this process. Well, one of our first steps was to say, look, we know we want to go down this net zero path. what is the best system to do that with? What is the most cost-effective solution? And we compared 3 different options. On the left, we looked at the central ground source heat pump system with heat recovery chillers in a mechanical room that send chill water and hot water to the building and use the geo loop as their source of heating and cooling. The middle option was what we had shown in our current design, which is the water source VRF and the heat pump air handlers and so forth. And then on the right was an alternative to that, where we use a heat pump in every single zone, right? Every zone gets its own little heat pump fan coil unit module. And what we found is that the VRF system was the most attractive from a life cycle cost perspective. Now that's all well and good that we picked the best of those 3, but those were all net zero, right? What does it cost to build net zero compared to a conventional business as usual high performance design? Well, we did spend almost $9 million premium on the geothermal bore field and advanced controls and the VRF systems and triple glazing for the envelope. So absolutely, there was a whole bunch of premiums we spent money on. But we also saved almost $9 million on reduced floor-to-floor height, reduced mechanical space, eliminating perimeter heat, smaller air handlers, getting rid of the conventional chiller plant, on and on. There was all these savings. When we compared what you would normally build versus what we actually built, the net premium was only $130,000, and that was through a very detailed analysis, actually scoping out the alternative design and getting it priced by the CM. It ended up costing less than 50 cents a square foot to achieve net zero. So with the utility incentives, where the utility incentives were over $900,000, it ended up being a first cost savings to do net zero. So that seems like maybe that's a one-off. We got lucky, right? Let's try another project. All right, here's maybe an even more challenging job. This is Boston University Center for Computing and Data Sciences. So this is a 350,000 square foot, 21-story high-rise building in a dense urban environment. It has a lot of the similar features that we saw on Chelsea Soldiers Home, but some key differences. So it has a great envelope with triple glazing and exterior shades. It has the dedicated outdoor air handlers. You recognize our little dual wheel trick here showing up again. We have fan coil units and fan powered boxes serving chilled beams throughout the building. We have a geothermal loop. We have peaking for our chill water plant. We have a water cooled chiller plant to handle the peak cooling load. We have our heat pump scroll chillers. That's that. In the last option, we have that left-hand choice of having a centralized heat recovery chiller system that sends chill water and hot water out to the building. And then we have electric boilers for peak and backup, and that means there is literally no gas connection to this building at all. There was a lot of focus put into the envelope. It was tuned by orientation and by depth of floor plate to have different amounts of glass and different amounts of shading and different shading geometry. We've got our friend here, our dual wheel for ventilation heat recovery. And then on the floor, most people think of chilled beams as a great solution for ultra low energy buildings, but unfortunately there's one fundamental flaw with a chilled beam. In a typical chilled beam system, you connect the chilled beam through the ductwork all the way up to the main air handler. So if your air handler is not running, you get nothing at the zone in terms of heating and cooling. So let's say you're unoccupied for a portion of the building, you're still having to blow air into that space from the main air handler. And usually if it's a 100% outdoor air handler, you're actually ventilating those spaces that nobody's in just to maintain temperature. Like the sun is setting and it's pouring in the evening, but nobody's there. You're wasting a huge amount of energy. So instead, what we did was we added these fan-powered boxes that sit between the air handler and the chilled beam, and they decouple those two things so that you can ventilate just as much as you need to, and you can heat and cool just as much as you need to by blowing air through the fan-powered box. And what that gets you is an ultra-low energy design, but also low maintenance, right? Because you don't have 30 fan coil units all over the space. You have just 7 of these fan power boxes per floor that then distribute out to all the chilled beams. All right, so how did we tackle geothermal on a tight urban site with such a tall building? Well, normal geothermal systems go down about 500 or 600 feet. We went down 1,500 feet, so 3 times as deep, to put in more heat exchanger area, more borehole area to get more capacity out of that ground. So that required a change from a conventional HDPE U-bend geothermal pipe to what you see on the screen here, which is a RYGAN high performance geoexchange system. It's a pipe within a pipe where the outer pipe is a high pressure capacity system. It can handle those tall heights of 1,500 feet in terms of pressure impact potentially. And then it also gives you a higher thermal performance because the inner pipe where the water goes down is insulated. You can see that on the bottom. I'm holding that in my hand. That's the EPDM material, so it's a more insulating material. And the water goes down the inner pipe and then it comes out into the outer pipe and on its way back up, and that's where it's a thinner walled system. It's exchanging with the ground, so you get higher performance out of that. So in summertime, we're gonna make that ground loop hot. We're gonna send heat into the ground and heat up the ground all summertime, and that's gonna allow us to use the ground as a cooling source. And then in the wintertime, on the next slide, we're gonna pull all that heat back out again and use it in the building. On the next slide, you can see the bore field layout. We have 31 boreholes, and 4 of them are actually under the footprint of the building, because all we had to work with was this skinny little alleyway in a corner park around the edges of the building. So similar to the previous project, we slashed the energy consumption of the building compared to the baseline. And BU is installing a bunch of solar arrays around buildings on the campus. And a certain percent of those solar arrays on campus is going to be attributed to this new building. And so that gets us from the 39 down to the 25. And then to get all the way to 0, BU has entered into a virtual power purchase agreement, a long-term contract with a wind farm developer in South Dakota, where they can offset the entire energy consumption of their whole campus and actually do it in a dirtier grid than you would see in Boston. And so if anything, it's a bigger carbon credit than if you had built the wind farm in Massachusetts. So it actually is getting them to a truly additional carbon neutral net zero building on day one. The real question again is, what did it cost? Probably spent a pretty penny, right? Well, we sure did. We spent over $9 million just drilling the boreholes and putting in the pipes. Huge cost to drill those 31 boreholes, but we were able to offset the majority of that cost with our much smarter investment in the building systems. So through reduced size of the air handlers and duct work and all of those costs and all the space savings associated with that. I mean, you think about what it costs per square foot to build a high rise in Boston these days. Every square foot you don't have to build to house those mechanical systems is a lot of money saved. And so this was the most rigorous life cycle cost analysis we have ever gone through. The real estate trustees on the board for BU a lot of them are developers, and so they had a very critical eye to this process and understanding what are the real costs, what are the real trade-offs, and it ended up being less than a 1% premium on construction compared to the conventional baseline design. So speaking of developers now are even moving down the road towards carbon neutral. So Alexandria Real Estate, we've been working with them on a project at 325 Binney in Kendall Square in Cambridge. It's a 500,000 square foot core shell developer lab building designed to be as flexible as you could ever imagine for any tenants that might use it for life science research. These are some of the systems that are in the building. We have advanced heat recovery for an advanced glycol runaround system. Starts with a K, for those of you that are familiar, to minimize the load on the heating and cooling from the ventilation air. We're requiring the tenants to use fan cool units in all the zones so that we, again, fully decouple space conditioning from the ventilation rates. We do have a geothermal system for heating and cooling as a part load system. But the even bigger driver for decarbonizing the operation of this building is the heat recovery chillers that we tied into the exhaust heat recovery system. So it's basically like a supercharged exhaust heat recovery system. This is a picture of our friendly heat recovery system from Convecta. They have really advanced coils that they can capture the exhaust air energy with. And we're really taking that approach to the next level. So the next slide, you can see On the top is the diagram of the exhaust air handler. On the bottom is the supply air handler bringing fresh air into the building. So you can see there's a heat recovery coil in the exhaust air handler in pink, and then there's a coil in the supply air handler down at the bottom that does the preheating of the outdoor air. Now, step one was to add a second coil to the supply air handler that does free reheat in the summertime, so it does wrap around the cooling coil. Step two on the next slide, and this is getting pretty unique. This is one of the first in the US to do this. We're intentionally frosting the exhaust coil. So that means when it gets below freezing in the exhaust unit and you're trying to pull all those BTUs out of that exhaust air, we're not going to back off on the heat recovery. We're actually going to keep pushing it harder to pull the heat out of the exhaust air, even letting the coil frost. And there's a sequence where the coils frost and defrost, and you can get a lot more BTUs out if you're not limited by that fear of frosting the coil. And then on the next slide, to fully utilize that, we're boosting the system with a heat pump chiller. So we are making that glycol ultra cold on its way to the exhaust unit so we can pull even more BTUs out of the exhaust air, and then we're injecting that heat back in on its way over to the supply unit. So this is really the ultimate in exhaust heat recovery systems in the world. Now, we did look at a series of different solutions like we do on all projects, make sure we're advising our clients and they're making a wise decision financially. So we looked at ground source in option 1, we looked at air source in option 2, we looked at exhaust source in 3, and then we looked at hybrid options in 4 and a few others. On the next slide, you can see all of these get to these incredible reductions in fossil fuel consumption. But it's interesting to see that the ground source, which people kind of often think of as like the ultimate for fossil fuel-free buildings, when you have a building that's so high energy as a lab building and has these huge peak loads, there's no way you're going to get a bore field big enough in a dense urban environment to handle the peak loads. And so because of those limitations, we couldn't quite get to the 90% fossil fuel reduction mark with the ground source alone. The air source and the exhaust source, either of those, depending on how much capacity you put in, can get up to this 94, 99% fossil fuel reduction range for building heating. This analysis happened to have a lesser capacity in the air source, so it didn't get as high as the exhaust source, but either one, you can just put more modules in and get more reduction. But the next question was, how much does this all cost, right? It always comes back to that. So on the next slide, you can see we compared a conventional design on the far left to these 4 advanced ultra-low fossil fuel options, the ground source, air source, exhaust source, and the hybrids. What you do see here, though, is there's one more option in the middle, option 0B. That's the second one from the left. That one is actually the cheapest to build, and it's pretty efficient and pretty cheap to operate too. So what is that option? Well, that's kind of the halfway point. That's where you say, all right, we're not going to do the old school, not very efficient building. That is actually expensive to build and operate. We're going to go and then take all the low-hanging fruit, all the things that are inexpensive or maybe even save cost, and we're going to bundle that up into a strategy that gets you to a very high performance design, but it's not ultra-low fossil fuel yet. And then you take the step of reinvesting into the heat pumps and the more advanced technologies to really minimize the fossil fuels. And that's where the price swoops back up again and ends up adding cost. So that's an interesting dynamic, right? You can stop halfway and actually run to the bank smiling with your cost savings, or you can take that and reinvest and go into the carbon neutral path. And ultimately, all of these options to the right are cost effective from a life cycle cost perspective. You can see there's millions of dollars in net present savings. So they're all a good decision financially. It's just a question of whether you want to stop halfway with the most dollars saved or do the next step towards the environmental benefit. You can see though on the next slide, even those more advanced options are below a 1% construction cost premium compared to the conventional design. And on the next slide, you can see ultimately Alexandria selected a hybrid between the ground source, which they had committed to the city of Cambridge to include in the design, and this advanced exhaust source heat pump system. What that means is as the building operates, you're really using the heat recovery and the geothermal system to slash your building heating from fossil fuels. On the right-hand side, you can see there's the red, which is the gas heating, just that tiny little sliver. It's almost gone. On the left, you can see there's just a few little blips where the red gas heating is kicking in to handle some peak loads. One other thing to see here, though, is it's got in pink the humidification. And in green, there's the electric humidification, and pink is the gas humidification. So this building was in design during COVID, and they really wanted to be able to show their potential future tenants that this was going to be an ultra healthy building. And we know that humidified buildings have lower transmission of viruses, so humidification was added to the design partway through. So that, even though we are partially electrifying that humidification system with some electric pony boilers, there is still that peak humidification load in those really cold, dry winter days. So there will be some additional fossil fuel consumption for that need. But ultimately, you can see we've benchmarked a whole series of labs that are similar all throughout Cambridge based on the BUDO publicly available data. You can see in yellow is their electric consumption and red is their fossil fuel consumption. On the far right is the projected for 325 Binney. You can see in bright green is their commitment to buy renewable power so that even their electricity will be carbon neutral. At the very bottom of that is that dark green little sliver. That's the fossil fuel for heating. And on the top in the hatched diagonal lines, that's the fossil fuel for humidification. But ultimately, just in terms of building heating, we're well into that 90%, even 95% fossil fuel reduction. So this is definitely achievable even for these large high intensity lab buildings.